we kind of jumped into reviewing thermal analysis projects. I only took a few classes of this in school, right? So everything I've really learned on this has been from getting reviewed and, reviewing the codes and stuff like that. So from heat is energy and it's trying to pass from higher state to lower state, right? So what we're measuring in facade systems is as we're turning on our mechanical systems, that heat is trying to get outside. And we want to measure how fast it gets outside. And we want it to get out as slow as possible. It's kind of the real zoomed out view of what's going on with thermal analysis.
One of the big things that's going on right now in the on the East Coast, it's being driven by code, and it's the energy code that's coming up, should be active 2024, 2025, where they're doing a heck of a lot more for following the paths. They call it bridging. So it's going to have detailed analysis of bridging that occurs in between facades and the regular structure. So I think that that's an important part of, we're in a good spot, if we can do some of this and add that on to, part of our services. But that's where it's going. That's where the industry is going. Go ahead.
So kind of with the big zoomed out, to just elaborate on what Stuart's saying there with bridging, that's kind of what we're looking for in our wall systems because, energy doesn't have a thought process, right? It just follows the path of least resistance. So if you got a wall, you got insulation here, and you got metal here, it's going to funnel to the metal. Or like on your house, it's funneling to the studs as much as possible. And that's how it's kind of trying to get out. And so that's what we're finding. We're trying to find what is the bridge in the system. Can we fix it? Or just in general, how fast, U factor is how fast does your heat transfer through your system? You want it to happen as slowly as possible. So code on this is NFRC 100. There's so much I've gotten into with the consultants on that. It's a code and standard that we want to stick to, but it shouldn't be thought of as like the IBC.
Reference.
It's more, it's like a reference standard. There's some stuff in there we definitely want to kind of stick to because NFRC 100 is the governing body for like Conair, Tube Light, all those guys who are their systems. They're going to follow the NFRC 100 to a T to get their systems passed. And basically, there's 3 stages that they have to go through. They have to get it simulated, which is what we can do. They have to get it tested, and then they have to get it. They have to have a third-party person put those together and make sure they line up. And so that's kind of what the big companies do. All we can do is simulate, which is calculation.
Why would they have us do that rather than just go to a big company?
I think they would like to come for like the structural and thermal part. Just like a one-stop shop situation, I think.
So they know they're still going to have to go test and have somebody put it together, but preliminarily we'll do the structure and the thermal.
No, yeah. I mean, a lot of these are tested, right?
Yeah. Ultimately, whenever we've got the stick-built systems that, all the manufacturers have, they've already gone through some testing. And also they've done the thermal calculations. They already have packages of those to be able to submit. Where we really get involved in it is if they have unique applications or if it's a custom type of a system and nobody has done any types of calculations with it.
Yeah.
And so in the past, that's kind of where Gorney has actually gotten involved in it. He's been able to do, some of the thermal modeling on these custom systems. And kind of show to the architect it's passed up the chain as a submittal. Yeah. Usually it's in the specification requirements that, a thermal analysis needs to be done and submitted. In a lot of cases, the thermal analysis specs that they usually call out, they'll make reference to you have to model it associated with like the perimeter boundaries a lot of times. Sometimes that's in there, sometimes it's not. And that's kind of a big question of, how do you adequately do that? Because if you're not really showing this against a boundary that, it interfaces in some way, then you're really not doing the whole thing that needs to happen. So that's kind of been some of the discussions in the past
And then the U value, isn't that just like 1 over the R value?
Yeah,
Yeah.
it's the inverse of the R value basically. But yeah, so back to what I was kind of getting into, there's the 3 stages. There's simulation, testing, and then there's a third-party consultant that lines those together. Simulation is the only thing we can do. That's the calculation. Answer your question, Carrie. The only reason they would come to us over going to like an ATC or somebody who does that is on custom systems usually. Yeah, just because it's very expensive to get it tested. So if you got a custom system that you're using on one job, you don't want to spend all the money to get it tested and go through the whole deal. You could just get it simulated by us and see if the architect will approve it.
Custom system stick built is the sweet spot.
Custom systems usually are unitized. At least when I've seen the custom systems, they're always they're unitized systems.
Okay.
They're for like the bigger buildings that, like, at least from my experience, it's a taxi building is a custom system. 65 Franklin was like a custom to them system. So it's just stuff that's not like Conair, YKK, Tube Light that they're trying to sell repetitively for a bunch of different things. Okay, so basically our software that we have is Windows. It's called a window, literally window, and then Therm. And so Therm is going to model our parts and pieces. I'll kind of show you how I did that. And then Window is a program that kind of combines everything together into one bay or unit. That's the glass on this one. So essentially, again, I'll keep it short. I wrote a whole document on how to use these programs in detail and like a lot of the stuff we're talking about in the shared area. So I won't go into like super detail because we have that available. We can kind of get into. I'll just kind of try to do the truncated version of what we're doing. So basically, this project is a unitized project. It's repetitive, 2-story around the entire building. This is one unitized unit and this is one unitized unit. They come together and basically with a thermal analysis, again, we're trying to find how fast the heat flows through the system. So we have to find the thermal properties for each part and piece. And so every unique part and piece. So the unique parts and pieces to this one, I kind of heard Stuart describing, we have the, top of the curtain wall with the parapet system. This is kind of a weird area where technically our curtain wall is here, but it interacts with the parapet. And so in this case, the design team specifically asked us to model the parapet system to see what happens back here and how the heat flows back into the system, because they call this essentially us. And so that's a unique situation where you've got a couple of horizontals, you've got an insulated metal panel system, and then it comes down into a DLO. And so I modeled that entire head system together in Therm because I'm just seeing how the heat transfers from inside to outside through that whole deal.
How are they enclosing the back end of the parapet? So that's like
it's just light gauge framing. I don't know. This must just be E.F.I.S. or something. I'm not 100% sure exactly what this material is.
what's that right behind that horizontal?
That's roof insulation.
No.
Fire stop.
Firefighting.
Yes.
So you don't include, or do you include stuff that's part of the parapet as part of the U value?
Yeah, I used for just this, usually on normal situations, I lean towards not including surrounding materials because we've had consultants tell us not to do it. But in this case, the consultant and design team asked us to review it. So yeah, basically it's cold form metal studs, insulated. And yeah, I'm pretty sure I just used E.F.I.S. For something like for that piece.
And this is kind of a part of, where I was talking before, a lot of this is up to the architect, if sometimes they spell it out in the specs that they want to have the surrounds modeled as, along with it. A lot of times they don't though.
Yeah. And it's tricky because where do you stop on some cases? I've had other ones where we've gotten into battles with them where they say, hey, use surrounding structure. But then it's like, it really is. There's no clean line like this where you say, all right, you got the parapet cap and you got roof insulation and, all this is probably good. But what's happening up here, that's a clean line kind of when it's just like maybe a jam condition, you got wall everywhere. Like, what do you stop? Like, you just model the whole building? No, someone needs to take over from there, a different contractor. So it gets tricky with that. But so yeah, that's the head condition. This one, we have a weird midspan condition where we have a walkway. I'll get into why that's important being attached to the curtain wall. But basically you've got vision glass and then spandrel glass. So 3 different spandrel glass conditions and some vision glass conditions. And then you got the vertical mullion condition. So typically on a typical project, it would just be, 1 vertical mullion on these unitized type projects. But on this one, I also had to model where the fin was because I wanted to see what happened there. So kind of getting into that. And I'll go into the models here, but usually I kind of get right to the results up front so you can find that quickly. But basically, again, truncated, long story short, we find the U factor for all these parts and pieces with therm, and I'll show you that. And then we do an area weighted average of how much those parts and pieces, how much those are a sum of the whole is what we're doing. So center glass, all these different unique conditions, I find the U value, I'll show you. And then you plug it into this sheet, find the areas of each. These are the U values, the sum of the total area, and then that gives you your area weighted U value of the assembly. So it's like looking back at something more simple, it'd be like taking your wall at your house and saying, I got studs, I got insulation. Has anybody taken like heat transfer thermal in school? Yeah. So it's like a parallel path. And so you take the inverse sum, and that's how you find your overall U value of your wall. That's essentially what we're doing in a little bit more of a complicated assembly. And so this is therm output. So you kind of recognize that's my head condition with all the insulation. And then this consultant was a stickler of making sure we reported all of our information. So I think it looks better that way. So I started doing this. So this is all the materials that we used and their thermal conductivity, how fast each one of these materials allow heat to transfer through it. Again, the program does the work of doing that math of like, okay, what's this assembly's factor? This is the heat map that it produces. So that's your overall U factor is spit out essentially here.
This is out of therm?
It's out of therm, yep. And what's important here with the heat map that it's spitting out, so the main thing therm does is find your U factor. But the other thing it does is this heat map, and where the heat map is important is for condensation resistance. And so essentially condensation is, you have a cold cup in the room. If that cup, the outside temperature of your material is below the dew point temperature of the room, it'll condensate. And so we need to find out, does the heat pass through quick enough to where it allows the internal materials to get low enough that it gets below our dew point temperature for the room. If that happens, you get frost and condensation on the inside of your metal. So that's another thing that we're looking for on that. So you can kind of draw, really hard to draw with Bluebeam. I don't get why the program doesn't have this if you can plug in a dew point temperature, but basically you will need to look at your heat map and see, okay, 34 degrees is, roughly when it starts to get dark blue. And you kind of can go through here and draw, I forget what that line's called, but there's a line that says, okay, nothing inside really gets to blue. And so we're okay. We don't have condensation issues.
What about on the horizontal below? So that big blue.
Yeah, it starts to get to where it gets blue on the inside, but I went through, and when the good thing about therm too is you can go through and put little thermometers.
Oh.
And so you can say, okay, this, I can't tell the color, just eyeballing it. So what's the actual temperature here? And all this was right at above the dew point temperature. So still okay. And then one other important item that's more of like a details item when you're going through this, you have to label all of your boundary conditions in therm. And so, and all that really does is it tells you what's included. factor number. So like I said, when we're doing our area weighted average of the entire assembly with that spreadsheet, this is also doing an area weighted average of what you tell it the boundary conditions are. And so solar heat gain coefficient exterior, don't ask me what solar heat gain coefficient and visible light transmittant is exactly. I don't under
Go look it up.
Yeah. It's just something. So it's something that I let the program kind of handle ultimately. So, but basically I need that for window later because it needs to know how much of this frame is on the outside of the building, basically. And so I said all of this, and then the top is on the outside and then the back.
It's normal. They have have a team of the saying. We already have like an SHGC value, like a thermal analysis. Now incorporate that there. Will it give you the same? I mean, how does it pan out when you have already have SHGC value for your glass alone, and then you put it
It's a good question. I forgot to explain that. So there's some back and forth between window and therm. And so window, you have to start off in window, and this is more in the details document deal, but you have to start off in window and you plug in your glass. Then that gives you the solar heat gain coefficient of glass, visible light transmittance, U factor of your glass. You take that and you save it and you backwards import it into therm. So this piece of glass in therm is the actual project glass. Yeah, so that's a good question.
Will that typically line up with like a insulated glass manufacturer and their data that they have for the glass? Will it, I mean, it's okay.
So in
Pretty spot on.
every year, before you do any project, I guess, there's insulated glass database or whatever, IGDBA or something. You have to have that as a program as well, and you update that, and that goes immediately into window.
It draws from that database.
So it has like thousands. So
Right.
every manufacturer has like an exact piece of glass. So you have to go through. Sometimes it doesn't have the exact because there's a custom layup or something. But you have to go through and kind of piece all the different pieces together. Like cardinal glass, for example. Let's say I've got a 3-light layup, a 3-light IGU. Cardinal glass will have a piece of fully tempered 1/4-inch glass. You can put that in there, and then you can put your airspace, and then you can put, you can kind of piece those assemblies together. And then on top of that, there's going to be some sort of like film on it. Cardinal glass or whoever, Pilkington, they all have a certain type of film. That's the trickier one where you want to have the right manufacturer because there's, I found there is some proprietary stuff going on where you'll get little differences between Cardinal and Pilkington.
Yeah.
And so you got to kind of piece your IGU together that way. So yeah, insulated glass database, do it into window, and you pull that out of window and put it into therm. And then yes, you'll have essentially that window portion down here for your IGU. Because all you're looking at in therm is really the frame. Should explain that too. It's mostly the frame and how that interacts with the edge of glass. And so like I was getting into, I told the program, this is all the exterior. This is frame, basically from horizontal up, because even though this is a spandrel area, it's metal panel, so it's going to act similar. It's aluminum framing essentially. This is edge, because edge has some unique stuff going on, edge of glass, because you have a spacer. So you have to basically tell this, hey, I've got either a stainless steel spacer or a warm edge spacer, and that interacts with your frame a little bit differently. And so when the program runs it, it'll give you U factors for each of those things in case they're important. The main one that I use is the solar heat gain coefficient exterior for when I'm using my overall system area weighted averaging, because that's for the entire assembly. If it becomes important and you said, I'm so close, I need to get rid of, will a warm edge spacer be better than the stainless steel spacer because my overall U factor is goofy? I can go look at that and say, okay, if I use a stainless steel, this one is a warm edge spacer, but let's say it's stainless at 0.29. Okay, it's stainless at this. What happens if it's a warm edge spacer? Does it do that? And then what's it do to the overall U? So that's kind of why you break that out.
Does it only have two different options, a warm edge spacer and stainless steel, or is it, are there more?
You can do whatever. Yeah, in therm, you can do anything you want.
You can identify a spacer that's a proprietary, type of user values or whatever. Okay.
Yeah, you can import materials, because ultimately when it imports this glass from Windows, it asks you, do you want to import a spacer automatically or do you want to draw in it?
Okay.
And so a lot of times I just draw it in, and this one I had to, because it usually when you import it automatically, it assumes it's stainless and you got to go play with it. So I just drew it in.
Does it allow you, I mean, the gasket is just like a rubber gasket most of the time. Does it allow you to put information regarding the gasket that separates the glass and the aluminum?
Yeah, so that's the purple here basically.
The other purple too,
the exterior.
and the interior.
Yeah, you have to basically every single piece of this thing,
Yeah.
you've got to define and draw. So without getting too much into that, it's not as much like Shape Builder where you just import a deal and it does it. Sometimes that works, but a lot of times you have to draw all these little rectangles.
Like nodes
Yeah,
and define
you kind of got to do a polyline deal.
yeah,
So it can be kind of,
and define the properties, like the permanent properties of that element.
they have a bunch in there, but you can make new ones and define their thermal conductivity. And yeah, so you have to define all this stuff.
And from the little that I know about thermal, because I know like maybe 5% of what you know. My understanding is center of glass is the best thermal part of the whole frame. Edge of glass is where we lose all the heat.
Yep.
Right.
Yeah.
Or the cold gets in, or the cold comes out. Like that's the thermal bridge on a right. Yeah.
So I don't know hardly anything either. He's really, he's the guy. He knows all this stuff. I do have an important note that I just wanted to stop on because we're talking a little bit about spacers. So in the past, whenever there have been failures of systems, many times it ends up being an issue with a custom spacer and how that's operating. So I just want to let you know for the future, these custom systems, be very careful about the spacer associated with it because that can lead into some tremendous lawsuits.
What all the just it's too stiff? Does it tear?
All I'm saying is it seems like it's always coming down to the use of a new proprietary spacer or, something. And ultimately that has a huge, impact associated with it. Because if you can imagine, that has on the therm analysis, it's relying heavily on that edge condition there. And if it doesn't end up exactly right with all of the environment that goes on the outside of the building, that edge can end up condensing. And then all of a sudden, then you got problems with people complaining about condensation on their windows and all the other stuff that's going on. So it's a big deal.
So it's not necessarily a structural concern, but sometimes it could be, I guess. But
I'm just saying, if we get into this, this is where a lot of the problems arise from. And there have been some spacers that I have seen out there in the past that have gone away because of issues that are associated with them. They get into lawsuits and go away.
Next thing I remember is at the Glass Expo, it seemed like there was like a ton of different spaces.
Yes. Yeah. Everybody's trying to develop something that helps out a lot, but be very careful.
And we watch how they're putting it.
Yeah.
We actually attend
Elko.
like a
Yeah.
Trimco.
Yeah.
You can kind of see what we're talking about. So both your especially center glass definitely does the best. And then the spacer is the reason why thermally, what I've seen the spacer is really important is because the reason the center glass is your best U value is because it's vacuum sealed. And so the program, at least that's what my understanding. And so the program is accounting for the vacuum seal. Because I had this conversation with a client on this project. He said, oh, well, he wanted to replace a cold form of the whole project. And so the architect was having trouble getting a U factor to work out on like a little curb. that was like insulated curb with cold form metal studs, and it had a sentry panel on the outside. I said, oh, let's just replace that with curtain wall. We could just infill the curtain wall with the sentry panels, but we'd replace all their stud work with curtain wall. He's like, that'll be better because you said my U factor for the curtain wall was 0.2 whatever. I said, no, that's because a big chunk of it is glass.
Yeah.
And so you can see on here, like this is the glass, and you see my, line or whatever, we're all orange and green. This is metal paneling, immediately starts dumping back into like it immediately starts shifting back into your insulation. Like this is all insulated. You can see your line dumps back way further. And the reason why I've read or whatever, it is the vacuum seal that helps you with your DLO. And so that's what I explained. I was like, it is only if you completely replace this with glass too. And yeah, so.
And argon or vacuum seal has no impact. If they add argon to the.
Argon's a little bit better, but
Is it?
I guess they still is sealed in some way. So I guess it's a good point because it's not exactly if they're filling it with argon, but it's sealed off.
Yeah.
And so.
So whenever we call it an airspace, it's actually often a vacuum inside the glass.
Yeah.
Well, and I guess that's why there's a load share. Would that be because there's a load share?
Yeah, because that's why I thought or maybe I'm using the wrong term. It's sealed off to the environment, but yeah, there's a vacuum, so we can kind of assume that it's going to pull the other piece of glass, right?
Yeah. I mean, ultimately, that's what that seal is around the edge. They'll vacuum that out through some ports that they have identified in the edge seal. And then either that or fill with argon, through those same ports. And they're supposed to put plugs.
Yeah.
And those plugs are an issue too, in being able to get that.
The main reason for the argon is what, thermal or?
It doesn't conduct, the same. And so it adds to the thermal value of the.
That's the main purpose of why people use argon.
Yeah. And for what I understand, it's not all that much. It's not a big, it's not a big deal.
Yeah.
And the argon has a way of leaking out over time. Supposedly, it's shown that argon will essentially be almost gone over 10 years.
Is it harmful to humans?
What's that?
Is it harmful to humans?
Not in the amounts that's inside of it.
Question regarding that airspace. I mean, in order to improve the thermal capacity of the glass, they have increasing from 1/2 inch. Some people will go to 1/4 inch to 1 inch just to increase the thermal capacity. Will it help on this?
Yeah, I had that conversation with one of our other clients. They had a 3-light IGU. Just from running things, I was learning too. I ran it with everything in there, and then I ran it with the middle light completely excluded and just the bigger airspace. They had a 2 1/2 inch airspace and a 1/8 inch ply in between that, or 2 1/4 inch plies outside. So 1/4 inch ply, 1/2 inch airspace, 1/8 inch ply, 1/2 inch airspace, 1/4 inch ply. I ran it with and without that center 1/8 inch ply, and you get roughly the same U factor. So it's really the separation, like the distance, the airspace distance. So the extra piece of glass didn't do anything, but it helped a little bit when they had me look at it with a film on it. Okay, that changed things.
Does laminate help any?
A little bit, just because it's a little thicker, but no, it's usually the airspace of the glass that matters the most, and then a film. If there's like a E whatever coating, that kind of changes things.
Well, for the lower heat gain,
low E.
Yeah. So that's what I've seen is mostly it's the gap, it's the actual distance. But you can't just structurally too. You want to have the 3 when you get out that deep, because I would assume that it would just not. I mean, you can't really have that big of a seal without another piece of glass in there.
That space is a flimsy little thin, like 0.006 something metal. So if it's spanning 1 inch, it doesn't take much to. You could probably crush that IGU with your fingers.
Yeah. So basically, it's really repetitive after that. You go through each assembly piece and you find the U factor, and I pull those U factors up to that spreadsheet and find their participation. On this one, we had the big deal on this one was the walkway. So getting back to that, we had a walkway that essentially passes by the thermal break. So this is a huge thermal bridge because you got your thermal break of your system, but structurally it's a heavy duty walkway. So we had to attach back into the meat of the curtain wall system to get it to work out. And so you're past your thermal break. So it bridged like crazy. And we're still in battles about the condensation resistance of this because I said it condensates. The consultant said, just changed it, the exterior environment from 0 degrees to 14 degrees. And so the client's not comfortable with that. And yeah, so.
Wait. There's a walkway being supported by a horizontal mullion?
It's the vertical. There's a good detail of it. So this is the vertical mullion.
Yeah.
So the walkway dives into my unitized vertical, and then we have, bolted assembly to attach it back into the meat of the curtain wall here.
Walkway, like people walking?
Yeah, big questions around.
Yeah.
It's like open, and you just said like walkway, and it was like, hold on a second, what?
That's a whole nother lesson. Once I finish this, I can do, it's been going on for what, 2.5 years now. We're fighting with the consultants.
I don't think the walkway is like long enough. The cantilevers, how long is
This one is,
so 1 foot?
yeah, but
So-
there's another one on the other side that is out.
You be quiet.
Yeah.
Don't say that out loud, they're gonna wanna expand. People, so actually supporting live load from people.
Yeah, that's the big, I guess I will, because we're all structural engineers, you guys are curious. So that's kind of the big question is one side is small, like Ivy said.
Yeah.
The other side is 4 feet wide. And there's a balcony on one side of the walkway and a balcony on the other side of the walkway. And so this is meant to be for maintenance personnel. But the architect kind of tried to shove in a dual use without really getting it code approved through the building commission of, well, we want people to be able to pass from this balcony to this other balcony. And so the architect and design team want us to design for live loads, like full on like 100 PSF balcony loading.
With
And
a mullion,
Yeah.
with
and I
an
said,
aluminum
It's
mullion.
100 PSF live load on there.
that's what they wanted. I said, that's crazy. You can't support 100 PSF from a curtain wall. So we got them to back down to 40 PSF live load, which is elevated platforms. And so, yeah, it's been a whole fight, but we're still fighting it. So it's,
That's the first.
yeah. So that thermally created a lot of condensation back here when I used 0 degrees outside, because obviously we've got a thermal bridge, a big thermal bridge at that location. And so it's not a great solution, but it was the only thing, again, being a structural engineer, diving into thermal, we put an extra insulated sealed off back pane. So there's still some questions from the consultant about how that comes together on a unit size system and gets sealed off. We got to figure it out because there's no other way to not get it to condensate. That we went through a little bit of an extra detail on this project because of that issue. I won't go too much into this, but long story short, we took what I did, all the different parts and pieces to do area weighted averaging of the whole assembly. And we went to a company who does 3D analysis. And ultimately, all they did was take this one shot where we said there's a condensation problem, and they found the same stuff I did with therm, pieced all those together just for this part, and then they used a fancy like rendering program to kind of mock them all together. Ultimately, the better way to do thermal analysis, a 3D thermal analysis, what is it, STAD, or like one of the higher powered programs, but they require a lot of computing power. So we got a quote to get that done, and from another company, and it was really high. Those are backgrounds.
And that's that infamous or famous walkway, the one that you're.
Yeah.
So that one right there. Okay.
Yeah, that's the walkway.
Positioning, it's getting below the dew point at that, like the back member of the members.
Yeah, exactly. So this is all below dew point temperature.
So you would have some condensation on that face of the aluminum,
Yeah,
like
so
in the form of like little droplets forming inside.
possibly. It's kind of like it's the same, like thermal isn't, and I could be wrong, thermal isn't like like I said with the NFRC stuff, it's not like the IBC, where it's like, this is the law, right? This could redistribute. It could, see dry air or something. I don't know. It might not condensate, but program says it does. So I don't have any way to say that it won't either. I also looked at, because consultant said, hey, use the 14 degrees outside. Well, I was like, well, let me find some evidence. I pulled, because learning from Stuart, like, well, let me find evidence that we can't do that. But I looked at data from New York City for the past whatever years. I think it went back 50 years and it didn't get below.
Really?
Yeah, it didn't get below 14.
In Manhattan, like for the urban.
I was
Island
really
effect?
surprised because it's supposed to be
I'm
cold there.
surprised, yeah.
I was like, this will be easy. I'll see it. But no, I looked back at historical data and it never got below like 15, 16, 20 degrees. It's like the coldest.
If the urban setting has an impact.
Old feet, I don't know. That's it. Yeah.
So, or I didn't find it right. 'Cause it's not easy to find.
What if, because we have like, we're receiving the some clients, which are some are good, some are bad. The one that you turn is really that important because detailing, I think is very important on this, especially when you do this 3D. It should be like exact, like almost perfect to, what we're installing. So now in 2D, let's say if we got shop floor that's not that good, I mean, how do we model it in turn?
It's a good question. Most projects that I've seen, even if the shop drawings aren't great, you can get the AutoCAD files for all the parts and pieces and kind of mold them together and still do this. This 3D, to your question, the extra detail of the 3D analysis, this only occurred because I told the consultant he was wrong. And basically I said, hey, and I didn't say you're wrong, right? I said, hey, this condensates. I think we should do something about it. And the client, jumped on board with it and said, yeah, we should do something. I don't want to take that responsibility. And it turned into a big deal. Normally, from my experience, small experience, like I said, 4 or 5 jobs, this has not been required. And to help with that, Integro, they're one that we did a 3D analysis with, and they're a Canadian company that they have in-house thermal engineers. And so they kind of helped hold my hand through one of them. And it was not any of this. It was literally just this stuff and then the spreadsheet. And so, and they said that's all that they see required on most jobs, just to kind of like look at the overall deal. Most of the time you can still get your parts and pieces and get it. This level of detail, like I said, I've never seen it be required yet, except for because of this.
And maybe, I don't know if this is a generalization, but the quality of a shop drawing typically is representative of the size of the project.
Yeah.
Because if you're going to do a multi-story unitized, system, it's hardly, I can't imagine a very poor set of shop drawings that they just use like manufacturer parts and throw it together into no letterhead and just like whatever. Typically the higher, like the bigger projects that might require the thermal analysis will have very detailed shop
Yeah,
drawings.
custom end of things. will
Yeah.
Typically get pretty detailed.
Whereas the ones, some of the projects that we see, the 5, 6 frames, some of those shop drawings are put together with the information that's available on Conair or Oldcastle, and they just throw in like a whatever letterhead on it.
Are there any comments or questions from anybody online?
That's really good, man. I hope to get one of these projects soon.
Finished. Last thing we have to do with the thermal project is we take all the parts and pieces from Therm and we import it into a program called Window. And that one's really easy to do. You say jam, vertical, center glass, blah, blah, and it basically takes what you plug in and gives you an overall U factor for your assembly as well. So it's kind of like a second guess of your overall U factor. It gives the solar heat gain coefficient and visible light transmittance, the stuff that I don't really know what's going on 100%. And then this one is the interesting one that I relayed to the consultant as well. This number is a condensation resistance factor number. So Therm kind of looks at those lines of flux and magically puts some number to it. Even when you read it, it does say like, it's like an idea. It should be close to 100. The fact that it's at 67 is another thing that the program is saying. This is probably going to condensate. It should be, when I ran other stuff, it's like 99, 100. So
It's like a confidence in how it won't concept.
I know that we need to wrap it up, but just as one of the takes that I want to take up your lesson, higher R values means better insulation.
higher.
Lower R values means that your temperature fluctuates easily and travels from inside to outside.
So
The maximum is
think-
100,
that's for the condensation resistance factor.
Yeah.
but the maximum will be 100.
Yeah,
Yeah,
that'll say it won't condensate.
but for the R value, it's more like 1, 2, 3, 4. Like it's not a percentage, the R values, right?
Yeah,
It's
it's
BTUs per hour, per area times change of the temperature.
Well,
So-
for the R value, it'd be the inverse of that, right? It'd be the hour if it's squared.
Oh, the hour
or
per
over.
square temperature gradient or change over
Yeah, it's just inverse, yeah.
inverse of U value.
I always think of it as U value from school. R value is more like what Home Depot and them will put in their stuff.
Yeah.
U value is like, the way you think of U value is, again, it's like, how many BTUs are getting through this area? Like, how fast is it happening?
I think R value is just because contractors like to deal with whole numbers and
Yeah.
decimals.
So the lower, the lower this is,
I got
the
60.
bad it gets. I'll wrap up so we can get to the other meeting.
Good job.
Thank you.
Yeah, cool.
You switch to the whole
Really
screen.
good.
Nice job.
Yeah, great job.
Yeah.